Okay, again, we are delving directly into a new unit of study. The last lecture we went through Unit 9, which was that quantities and chemical reactions. And now we're looking at the way in which a chemical reaction is uh, actually carried out in a practical sense. We've done a lot of talk about how these starting materials go to these products in a chemical reaction, but we've never really talked about the practical aspects about a chemical reaction, how exactly those reactants are brought together to form products. Now, almost without exception, the chemical reactions occur in chemistry in a dissolved state. So we have to have our, if we think of our reactants dissolved into solution, into a solvent. So here over here we see that we've taken a chunk out of this here, we've dissolved it into solution. So we have two components to an actual solution, which would be a solvent and what is dissolved in it, known as a solute. So here's the two components. The solvent is what is doing the dissolving. That is just defined as the largest component in a solution. It is the majority component, almost again without exception. The solute itself is what is dissolved in the solvent, and it is almost always considered a minority component. There's less of it if we looked at the amount of solute and solvent. So when we think about solutions, we're sort of conditioned to think about solutions in the liquid state. But we can also have other types of solutions corresponding to the two other different states of matter. We can have gaseous solutions. Gaseous solution would be a gas dissolved in a gas. An example of this would indeed be the air we breathe. It's a dissolved solution of oxygen, nitrogen, argon, carbon dioxide, and so on, but it is indeed a solution. We just don't think of it that way. Our liquid solutions are what we look at most often when we think about a solution, especially the solvent being a liquid. Now, a solvent being a liquid can accommodate into it a solid, a liquid, or a gas as a solute. But again, it is because we have a liquid solvent, it is the one that we're most conditioned to think about. Now, lastly, we can have also a solid solution. A solid solution, like perhaps an alloy of a metal like brass, which is copper and zinc, that sort of thing. We don't usually work with them that much, solid solutions and gaseous solutions, but they do exist. And almost always we work with liquid solutions. And when we think of liquid solutions, we have to think about now the types of solvents that we're going to be using in these liquid solutions. And the solvents themselves usually fall into two categories. Here's a table of some common laboratory solvents. Generally, they'll fall into these two categories, which would be a polar solvent or a nonpolar solvent. Now, we're going to find that they fall into these categories. If you look at these examples of polar solvents, water is an example of a polar solvent, and we'll talk about why it is considered polar, as are others like considered acetone or methyl alcohol or something like that. We find much of the time in general chemistry that, and I think I've said this before, that our solvent of choice is almost always water. For whatever reason, that's the case. And it's because water will tend to dissolve ionic solvents, and we work with ionic solvents a lot for whatever reason in general chemistry. So water is much of the time the preferred solvent. That doesn't mean it has to be the only solvent. And now that we're talking about solvents, well, we have some examples of these common polar solvents, of which water is one example. We'll juxtapose this against some common nonpolar solvents, that of hexane, diethyl ether, toluene. These are examples of them. There are plenty more of them, but the idea of polar and nonpolar really speaks to what is the solute that they're going to be dissolving. And the solute that they're going to be dissolving, we have to tune solute with solvent, or we won't get them to the solute to dissolve. Typically, a polar solute will dissolve in a polar solvent. A nonpolar solute will dissolve in a nonpolar solvent. And we have a name for this, or a term rather, for this. Our term for that is considered like dissolves like. So, and that's if something is nonpolar solute, it is going to dissolve in a nonpolar solvent. It is alike. But if we had to look at the definition of it, we said if the forces, the intermolecular forces between the molecules or particles of a solute are similar to the forces between the molecules or particles of a solvent, the solute will likely be soluble in that solvent. Like dissolves like. So for instance here we have, in this case, two examples of water as a solvent. And in one of them, we're pouring into it ethylene glycol. Now, ethylene glycol is the major component of antifreeze, and it is a polar type of compound. Water is also polar, so as you can see in this picture, it looks like the ethylene glycol is indeed dissolving in that polar solvent, water. Whereas if we have a polar solvent, again, which is water, but we put in something nonpolar, something like motor oil, what we're seeing here, which is hydrocarbon in nature, we're going to find that that is not likely to dissolve. So unlike will not dissolve, unlike. In this case, you can see up at the interface here of the motor oil floating on top of the water, and indeed it is not dissolving into it because solute and solvent are not alike with respect to polarity. So another type of solution we looked at, or somewhat of a familiar one, are liquid-liquid solutions. And we talk about this concept of solubility, of a solute in a solvent. And this is almost just as an afterthought. If the solute is liquid, just like the solvent, well, we say that that liquid is miscible in the liquid solute is miscible in the liquid solvent. Again, here we have two solute and solvent which happen to be liquids which are miscible in one another because they are both, in this case, they happen to be nonpolar. I'm telling you that. You can't really tell from the fact that it's octane and carbon tetrachloride, but they are indeed both nonpolar, so they are miscible in one another. You could also say they were soluble or they were dissolvable, but liquid in liquid we tend to think of it as miscible. Again, just like last time, if we had a hydrocarbon in water, as we have over on the right here, these would be immiscible in one another, meaning they're not dissolvable in one another because in this case is gasoline, that's a hydrocarbon that is very nonpolar, whereas water is very polar. We can't bring in that like dissolves like, so those two would be immiscible in one another. So let's define some terms. Now that we're dealing with solutions of a solute dissolved in a solvent, we can say that a saturated solution. Let's look at this concept right here. Now, when we are dissolving a solute in a solvent, we can continue to do that. Add a little solute and stir it around. It will dissolve. Add a little more. Stir it around. It will dissolve. But it gets to the point where a solution holds the maximum amount of dissolved solute. So any other added solute to it, even with vigorous stirring, will not dissolve. It will remain as a solute. In this case, I'm assuming as a solid solute. And that is because the solution has become saturated. A saturated solution is a solution which holds the maximum amount of solute. So this brings up our concept of the solubility of a solution. How soluble is a solution, meaning how much solute can a given quantity of a solution take into it. So as here it says, the solubility of a solution means the amount of solute which can be dissolved in a fixed amount of solvent. We have to define the amount of solvent, whether in volume, whether in mass, but obviously more solvent will dissolve more solute, so we have to have a fixed amount of solvent, and then we can measure the amount of solute which can dissolve in it, and that would be the solubility of that solvent for a particular solute. Now, solutes are not all the same. Different solutes can dissolve to differing amounts or extents in the same fixed amount of solvent. Further, the solubility of a solute in a solvent is highly dependent upon the temperature of that liquid solvent. So here we have a graph here showing a number of different solutes and their solubilities in water. And look over here on the x-axis, we have increasing temperature. On the y-axis would be an increasing solubility in grams per 100 grams of water. So as you can see in both of these cases, we have almost without exception, indeed without exception in these cases, as we increase in temperature, we get an increase in the solubility of each of these solvents in that particular solvent of water. The effect is very pronounced. KNO3, you barely have to increase the temperature of the water at all, and it really increases the solubility of KNO3 in water. However, we can look at something like sodium chloride. Well, yes, as we increase in temperature, it does increase in the solubility, but not by much. And this brings it back to what I was saying about all solutes are not identical or identically dissolvable or soluble at various temperatures even in a particular solvent. So I'd like to get back to our idea of solvents being polar and nonpolar. Now, as shown here, water itself is a very polar molecule. We talked about molecular polarities in a previous unit of study, meaning we have a dipole moment to this molecule as shown here. Now, this dipole moment brings electrons towards this part of the molecule. The electron density is more up in this region of the molecule, and we have sort of an electron deficit down in this region of the molecule. Since electrons carry the negative charge, that brings this sort of area of the molecule down here, having a deficit of electrons, to be partially positive character. It's not a full positive charge, but it has partial positive character. That's what that sigma plus means. Whereas over on the other end of the dipole, we have an excess of electron density on the average. So that gives us sort of a negative character to that end. So we have a positive pole and a negative pole. Again, not completely not talking about an actual positive and negative charge, but we have positiveness and negativeness associated with it. This is why ionic solutes tend to dissolve well in water. We're going to take a look at that in a little bit more detail. So ionic solutes, well, we have ions. There's a positively charged ion. Since like charges attract, positively charged ions tend to want to hang out on a negative dipole. Negatively charged ions tend to associate towards a positive dipole, and in so doing, we end up with generally water tends to dissolve quite well ionic solutes. So let's look at this idea of an ionic solid dissolving in water, thinking for a moment what is going on when we're talking about the dissolution of an ionic crystal. Well, that takes an ionic crystal like we see here, this sodium chloride, we've seen that before, and essentially turning it into ions. So we have positive and negative ions which are separated. Well, in so doing, we have overcome a chemical bond, which is an extremely strong attraction. So how can water ultimately do this? Well, let's imagine a crystal of an ionic solid dissolved in water. And in so doing, it is continually buffeted by these water molecules, which we're looking at right here, sort of buffeting up against that crystal. And every so often, that buffeting will just for a moment dislodge one of the ions, one like a positively charged sodium ion or a negatively charged chlorine ion. Now, normally, these slightly dislodged ions would immediately go back into the crystal and remain in the crystal. However, once this happens, once we dislodge an ion, it becomes encased in a sheath of water molecules. So this is a cut through here, but it's really a spherical sheath. And look what's going on here. Here's a chloride ion, negatively charged in the center here, but it is completely surrounded by water molecules with the positive dipole, these Mickey Mouse ears, if you will, pointing towards it, because like charges attract. Now, it's not a full charge on those molecules, on those water molecules, but notice they are pointing directly, the positive dipole on the water molecules are pointing directly towards the negative charge on the chloride ion. And we get this spherical sheath around it. And since that chloride ion is now completely surrounded by this solvent sheath, if you will, it just floats away because it is trapped. That chloride ion is trapped. It cannot reassociate with that crystal of sodium chloride. The same can happen when we dislodge a positively charged ion, in this case sodium. What would happen? Well, it too immediately gets surrounded by a spherical sheath of water molecules, but look how they're oriented here. They're backwards from the previous one, where we have our negative dipoles on the water associating, or the water molecules associating with the positive charge on the sodium cation. So here we have the exact same thing going on as before, but look at all of these water molecules now are different. So the way they are associated towards the ion are different in both cases. Look carefully and you can see that. So in all of these cases, ion after ion gets shuttled away in these solvent sheaths. Eventually, that crystal of ionic solid will have completely been converted to separate ions, and they're all floating around in their solvent sheaths, unable to come back together to form that solid crystal. Okay, let's define some terms, because a solute, where we've gotten a little bit used to a solute being ionic, where we have a solution of dissolved ions, it doesn't have to be that way. We can have a solute which is non-ionic, meaning covalent, but it can still be dissolved in water. An example of this would be sucrose, or rather table sugar, which is a covalent compound made up of carbon, hydrogen, and oxygen, all non-metals, and this can dissolve into water as well, because the forces in that molecule are very much like water, very much like water. So that like dissolves like. Our sugar molecules can dissolve as well. They are not ions. They are just regular old molecules in this case. So we can pose the difference here between a solution of dissolved ions on the left and a solution of dissolved molecules on the right. So the way we name these is, if we have a solution of dissolved ions, it is known as an electrolyte solution. a solution of dissolved molecules, not ions, it is considered a non-electrolyte solution. So it's just a term. If you think of an electrolyte solution, well, it's got some dissolved ions in it. If it's a non-electrolyte solution, well, what is dissolved in it is not an ion. One salient feature of electrolyte solutions is that they can conduct electricity. So electrolyte solutions can indeed conduct electricity, while non-electrolyte solutions cannot conduct electricity. And here's just an example here. We have a closed circuit, and part of that circuit over on the left here is a dissolved solution of ions. That is an electrolyte solution, and over here we can see in that closed circuit, well, that bulb is indeed burning, so it shows that the circuit was closed. Whereas if we had a non-electrolyte solution, such as dissolved sucrose or table sugar, we have here on a closed circuit, that bulb, again over on the right-hand side, is not lit because that gap between the two electrodes cannot conduct electricity like the one in the electrolyte solution. So you may have noticed up to this point, this lecture has been very heavy on definition or terms or description. And that's the case sometimes. And we're going to find right now, we're going to be taking a bit of a turn. Having described all the salient features that we need to of solutions, now we're getting more into the practical stuff. We have to start thinking about what type of solution do I have? Not just what solute in which solvent, but we have to talk about, well, what if the question was, well, how much solute is dissolved in that fixed amount of solvent? I could have a very weak solution, or I could have a very strong solution, depending on the amount of solute dissolved in the solvent. The term we use for this, determining strong or weak solution, is solution concentration. The concentration of a solute in a solvent is how we are going to be looking at that. And we'll be looking at a couple of methods, a total of 3 by the end of this unit of study. But a couple of methods to start us off, ways of expressing solution concentration. And I'll start off with one that is almost an afterthought. This is considered mass percent. And as written here, it is more underutilized and it's more of an archaic method. You don't see it as much anymore. It has fallen to another way of expressing solution concentration, which is used much more, that we'll talk about. But mass percent still does rear its head sometimes. For instance, if you go into the drugstore and buy a solution of hydrogen peroxide, it'll say right on the bottle, 3% solution of this compound, and that is essentially in mass percent. So this would be a mass percent way of expressing that. It is underutilized. We hardly ever see that anymore, but this would be one example where that hydrogen peroxide is frequently measured in mass percent. Now, we've talked about mass percent before, but remember, this is going to be different because the mass percent we talked about before was the mass percent of an element within a sample of a compound. We're not talking about that anymore. Yes, it shares the same 2 words, but it's something completely different. Mass percent is going to be essentially plugging into an equation. And here is the mass percent equation as it applies to solution concentration. It is essentially the mass of the solute divided by the mass of the solution times 100. And there we go. We're going to get to like these plug and chug things because it's not as much thinking, say, as a classic dimensional analysis, which we'll get into eventually. But in this case, when you see mass percent of a solution or a solute in a solution, that's great because you're just plugging in numbers. Now, important to note, when we talk about that denominator, mass of solution, that means it's not just the mass of the solvent. A lot of people think, well, it's just the mass of the solvent. No, it implies the sum mass of the solute and the solvent. Very important to make that distinction because you'll get the wrong answer if you don't do it that way. So let's look at a simple example of a mass percent problem. And how would we know it's a mass percent problem? Well, probably because it says mass percent right in it. That would be an indicator. In any event, calculate the mass percent of sodium chloride in a solution of 15.3 grams of sodium chloride dissolved in 155 grams of water. What's the mass percent? Okay, here we go. Well, going back to the mass percent equation, we're going to find the mass of the solute and put that in the numerator. In the denominator, we have to be careful because that's the mass of solution, so we have to add the mass of the solute and the mass of the solvent. Just because something is dissolved doesn't mean that its mass goes away. We may not be able to see those NaCl crystals anymore, but the mass is still there, so we have to account for it. And then it becomes elementary, times 100, and we get a percentage. 8.98% is pretty straightforward. So let's now take a look at a more current expression of solution concentration, and it's known as molarity. Molarity, by far the most common measure of specifying solution concentration. We will be using this over and over and over again. So it's good to get ahead of the curve and start understanding some of its basic tenets. What is molarity? Well, the term mole is in there, so we're going to be dealing at least with moles of whatever we have in there. So it is moles of solute per, that would be a division line, 1 liter of solution. So it's making a statement, for every 1 liter of solution, I have this many moles of that solute is dissolved into it. It is expressed as, we have some units of measure here, and it is expressed as moles per liter, number of moles per 1 liter, so that makes sense. You see that division line for the per expression. And a way it's expressed sort of in an abbreviatory sense is as shown right here. The capital M with a line under it. Sometimes in some textbooks or whatever, they don't show the line. It's just the capital M, but it is shown as, I show it as an M with a line under it. That is considered a molar. So if I had 1 mole of solvent in 1 liter of, solute in 1 liter of solution, I would say that is a 1 molar solution. I'll be saying that a lot, just so you know. A 1 molar solution means that we have 1 mole of solute in 1 liter of solution. Solution. Now that's important. 1 liter of solution, because remember when I was saying in mass percent, the mass of the solute does not go away when it is dissolved in the solvent. The same can be said for volume to a great extent. If I have a volume of a solute and I dissolve it in a solvent, well, that volume doesn't go away. Even though it's in a dissolved state, that still has volume to it. So what we cannot do when we think about a mole, like say a 1 molar solution, is I can't just say, all right, I'm going to take 1 mole of my solute and put in a liter of solvent. Once that's dissolved up, that's going to be more than 1 liter. Thus, it would be 1 mole of solute divided by more than 1 liter, and it wouldn't be a correct way of creating a correct molarity. So let's look at the proper way of coming up with a 1 molar solution, or whatever, 2 molar, 5 molar, it doesn't matter. The proper way to do that, and this is the way to create a 1 molar solution of sodium chloride. The trick is we put in our solid, our 1 mole of our solid solute first. In this case, sodium chloride, 1 mole. It happens to be 58.44 grams. We could figure that out by looking at the periodic table. And then we put in water. And we put that water in to the vessel so that the solute dissolved, and this is a specific type of vessel. It's called a volumetric flask. And this volumetric flask is very skinny at the very top, and it has this mark right here. And that mark, that little line there, will fill it up with water right up to that mark, and that is exactly 1 liter. The skinnier that tube, the more exact we can get to being exactly 1 liter. Obviously, the vast majority of that 1 liter is held in here, but these are specially made to hold exactly 1 liter as long as it's right to that line. Then we are assured that I know I had 1 mole of my NaCl solute in there, and I know that it's a dissolved solution right exactly to the 1 liter line. So, the point I'm trying to make is it matters how we put these things together. So let's look at some example problems that you will likely encounter, types of problems you'll likely encounter. Certainly many of the problems in the problem sets on Blackboard for this course have problems like this. So let's look at some examples. Here we have, calculate the molarity of a solution made by dissolving 15.5 grams of NaCl, we seem to go to NaCl for some reason in these examples, in water to make 1.5 liters of solution. Okay, well, we're talking about needing to calculate a molarity, meaning we're going to need moles of solute. I don't have moles of solute, I have grams of solute. So we have to do that first dimensional analysis to convert grams to moles. Remember, when in doubt, convert to moles. So that's a dimensional analysis. What do we have? 15.5 grams of NaCl. What do we want? Number of moles of NaCl. How are we going to get there? Well, the molar mass of NaCl, where we can cancel out of grams of NaCl and come up with moles. Then and only then do we reach for our calculator and we come up with our number of moles of NaCl. So that's the number of moles that are going into 1.5 liters. But molarity is the number of moles in just exactly 1 liter. How do we fix this? Well, we take the number of moles that we have of NaCl and we divide it by whatever the volume of the solution is in liters. Just divide it. This forces it into molarity, number of moles per 1 liter. So it's really elementary at that point, because once we carry this out, we get 0.177 molar. So that M with a line under it means 0.177 moles per 1 liter of solution. That's the same thing as saying, really, 0.265 moles of NaCl per 1.5 liters of solution. However, by convention, we always bring it back to number of moles per 1 liter in order for it to be considered molarity. Let's look at another one. Here we go. How many liters now of a 0.114 molar solution contains 1.24 moles of NaOH? Well, this is actually a per expression. We're going to find a per expression in here. It is a dimensional analysis. Pro tip, in any sort of example problem which involves when we show a molarity. A molarity, if you'll remember, is a per expression in itself. So almost always when we see a molarity in a solution, we're going to pull that out and put it into a per expression, and probably, almost certainly, use that in the problem. Whenever a molarity is given in a problem, almost always it will be used as a per expression. Indeed, 0.114 molar equals, how would that show up as a per expression? Well, 0.114 moles of NaOH per 1 liter of solution. That is, so we have numerator, denominator, that's ultimately how we're going to use it. let's look at this more closely. That is, a per expression is a doorway, in this case between moles of NaOH and liters of NaOH. Well, look at what the question is asking. We have moles of NaOH solution, and it's asking how many liters. So of course we're going to use this per expression as that doorway. Now that we know this, we're going to do a dimensional analysis. And this is important because on that first question in a dimensional analysis, what do we have? We go searching for a number. And this problem has, well, two numbers in it. And I always say a whole number, meaning a numerical component and a unit of measure. That would be the 1.24 moles of NaOH. 1.24 moles. This 0.114 molar, remember, is a per expression. That's not what we start with. So let's see now, what do we have? Well, 1.24 moles of NaOH. What do we want? Some number of liters of NaOH solution. We know what that doorway is now because we pulled out that molarity and we forced it to look like a per expression. How are we going to get there? There it is. Notice I had to invert this from looking like this. I had to take its reciprocal, and that is because moles of NaOH then cancel out, and I'm left with liters of NaOH solution. That is what I want. And as such, it becomes elementary. We pull out our calculators, and we end up with 10.9 liters of NaOH solution. So let's look at another one. And sometimes we have to ask the question, what is it that we want the molarity for? Is it for an entire compound, like NaCl? So do I want the concentration, say, of sodium chloride? Or do I want the concentration of just sodium ion, not sodium chloride? It would be the same concentration in this case. Or what's the concentration of chloride ion in that sodium chloride solution? Again, that's a different question. So we have to be careful sometimes. And now we're going to look at an example based upon ion concentrations, based upon the molarity, the concentration of an actual solute. So we're talking about dissolved ions, so it would be an ionic solution, an electrolyte solution. It depends. Let's look at an example where we could have a different molarity of the compound than the molarity would be of one of its constituent ions. Well, an example would be, what are the molar concentrations of sodium, Na+, and phosphate, PO4, 3-, in a 1.5 molar sodium phosphate solution? So how do we go about this? So looking for the concentrations of the ions now. Well, let's take a closer look at sodium phosphate. If I have a 1 molar solution, there it is, 1 molar solution of sodium phosphate, let's see what happens when that dissolves into water. How many moles of sodium ions does it release? Well, 3 times what it was for actual sodium phosphate, because one of these breaks into 1, 2, 3 of these. So we could say if we had a 1 molar solution of sodium phosphate, that would be a 3 molar solution of sodium ion. Similarly, with phosphate, if we took PO4, 3-, that is a 1 to 1 molar relationship because there's 1 phosphate for every entire sodium phosphate molecule. So we have to be careful of what we're asking for. Indeed, what we're doing is we are creating a per expression. This is a 1 to 3 per expression. This is a 1 to 1 per expression. Let's see how this might be put forth. For sodium ion, what is the molar concentration of sodium ion? Well, we'd start with 1.5 molar sodium phosphate, and we're looking for the molarity of sodium ion. What's our per expression? Well, we just pulled it out previously. 3 moles of sodium ion per 1 mole of sodium phosphate. It reflects this 1 to 3 right here. And of course, we were able to, essentially, that's just multiplying this number by 3. And it's actually 4.5 molar sodium ion, from 1.5 times 3 to 4.5. Of the sodium ion. The same thing we can do for phosphate. We start with our 1.5 molar sodium phosphate, and we want to know what concentration of just phosphate ion. Well, again, we saw that before. It is a 1-to-1 molar relationship, if you will. Again, this 1-to-1 right here, which we saw. So that is reflected in the per expression. And that's, again, we're just essentially taking 1.5 and multiplying by overall 1, and it gives our 1.5 molar of phosphate. But look at this now. So it depends on what we're asking. We have a different concentrations here on the end of sodium and of phosphate. So are we asking, are we talking about the concentration of sodium phosphate? Are we talking about the concentration of sodium ion? Or are we talking about the concentration of phosphate ion? All I'm saying here is that it matters, and it would be good to pay attention to that sort of thing for, when we're potentially working through a word problem.